Hello everyone and welcome back to the Game Networks Architecture class. And basically we are getting pretty much close to the end of the semester, and we have discovered and discussed several really neat topics within this class. We started with looking at multimedia network architecture, and then the relationship of network architecture for multimedia systems and those for gaming applications. Then we delved into socket servers that are used for gaming applications, which are basically software applications that deal with taking care of your network connection to a server. And we started working with the Electro server, which is a socket server. The version that we worked this class with was version 4.0.6. And then we went through several applications, what are different techniques that you can use, the server concepts from chat rooms to zones to users to login to the Electro server object actually, and then we advanced so far through working with server or rather authoritative server applications through implementing real-time movement. And last week we worked with the here I am approach, or rather the frame-based approach, and we discovered that with the frame-based approach you can essentially synchronize your multiplayer applications and your multiplayer games so much. And we discovered that there are issues with working with frame-based approach. Now, the ultimate goal here is to achieve smooth movement and time synchronization through a time-based approach to create the synchronization between moving objects on several platforms and across multiple clients. One of the things that is critical to achieving this goal is that all of the clients would have to agree on what time it is that they are processing, or rather they're implementing and rendering a scene. When you think of this synchronization about what time it is, as opposed to where I am approach, it would be essentially a little bit more complicated. So with this, we would have to start talking about two key ideas and two key terms: the ping and the latency. And then later on I'll show you the clock example, the clock class that achieves uniform synchronization on server time. If you have ever worked with any kind of networking system, you probably have come across with the word ping. Ping essentially is when you send a small package, or a small packet rather, across the server to a client, and then or from a client to a server, and receive your packet back to test the connectivity of your network, as well as to test its performance. So if you want to think about this, in the picture here on top, you have a client and a server. So the client creates a small packet and then sends that packet to the server. The server receives the packet and performs a kind of mirroring application on it. It basically sends the packet back to the client, and through this the client will be able to achieve some sort of basic network connectivity and network performance evaluation. So if the time t sub 0 is the time that the client creates the message or the small packet and sends it to the server, and it receives it at time t sub 1, which client can, by looking at its own clock cycle, calculate those, you would be able to calculate the difference between the time received and the time sent, and that would give you an idea about the ping. So essentially the bottom picture on the left here also shows you an example of what happens. So t sub 1, which is the time that you receive the packet back from the server, is t sub 0, which is the time that you sent the packet, plus the time that your client creates and takes to process that, plus the traveling time from your client to the server. If you were sending it across the globe, it would probably have to go through a satellite, and so that's so much time that it takes. And then for the server to receive it, then the server would take some processing time, and then it would send it back to the client, which would take some travel time back to the client, and then the client takes some processing time to package back that packet and work on it. And this would be essentially the t sub 1, or the time that you received the message. So one of the issues when you're calculating your times on the server and on the client side as to how much it takes for the server to process your packet and send it back, how much for the client takes to create the packet and to receive the packet and look at it and read through it. You won't really have an idea as to how much it is essentially client takes or server takes, and it really depends on the load on the client and the server. Also, it depends on the amount of processing that your packet processing that your application needs to spend. And so usually you wouldn't know how much of it would your packet would spend on each side. But if you think about that, it's probably negligible with respect to how much time it takes for your packet to travel. So in essence, you can think of latency to be the half amount of ping, or basically one-way traveling time that it takes for your packets to be received and to be sent. So in order for us to proceed with our synchronization mechanism, I would have to make an assumption that the ping round trip basically spends, or your packet spends, half of its time going to the server and half of its time going back from the server and returning to the client. With this assumption, essentially, you can think of the latency of your network to be half of the ping value. In order to synchronize movements on all of your screens, your clients have to agree on the time. But instead of synchronizing with each other, they would essentially adjust themselves and synchronize themselves with the server. In this technique, the client sends a ping request to the server, and the server sends a request back to the or responds back to the client with a timestamp on it. And the client then will be able to determine from the timestamp on your message what the server time would be. So server time is essentially, or the time that your server processes your message is equal to the time that your client processed it, plus some traveling time that it has been essentially spending on it. So from here, you would notice that this offset would be the server time minus the client time, which is the time that you have on your machine, plus the latency. That's the half of the amount of the time that your message travels back and forth. So the timestamp that you receive from the server is basically the server time. You can know your client time by looking at your clock on your machine, or the software equivalent of it, and you will be able to essentially calculate those two measures. However, you won't have a mechanism to calculate the latency because latency is half of the round trip value. Alright, now if you look at the equation here on the second line, the green line, the offset equals server time minus client time plus latency, it is very important for you to get the latency value as correct as possible. Otherwise, the offset values that you would have is not going to be accurate. So there are several ways that you can calculate the value of your latency. And one special mechanism that your book suggests is to calculate your latency by sending several ping messages and getting the latency values and the offset values essentially off of those time differences of your ping. And once you have those several values, to either to try to find which one or what would be an average expected value for your latency that would be as close to the real values as possible. One way is to essentially calculate the average of those values. However, if you have several numbers, let's say that in this case, in the picture on top here, top left, if you send 1, 2, 3, 4, 5, 6, and 7 ping messages, and then for each message you calculate the latency, and if one of the messages is sent over, I don't know, a heavy traffic on your network, or maybe server or client were super busy, you would get a large ping value, which essentially half of that would be your latency value. So apparently the value for this message over here is essentially far off. So this would have been an outlier. So your latency usually isn't that high in this example. So if you average all of these, then you would get the average latency, which is not going to be very accurate. However, if you look at the median of the values of latency that you get over 5, 7, 10, 11, or how many number of packets that you send, and then discard those ping values or latency values that are more than, say, 1.5 times the median, then you calculate the average over the rest of these values, your latency calculation is going to be much more accurate. Apparently, this is just one simple ad hoc mechanism to get rid of outliers. If you were interested in doing a research project, we could come up with a more elaborate mechanism of calculating your latency by training a latency calculation mechanism and having the latency calculated every time based on that application. But this special example here should work well enough. Now, in your book, the author has created a clock class, and the clock class is included in the com.gamebook.utils.network packages that is coming with the applications and the examples for the book. And in today's class, you will see how this works in terms of synchronizing your server times. What you will need to do is you simply in your application create an instance of this class and pass it to your API for the Electro server, and just tell it which plugin you want to use, and then you start it. So an example of it, of the code that you would write, is shown here. So you create a reference for the clock, and you send the reference of your Electro server API and the timestamp plugin, which was a server level plugin that we installed a couple of weeks ago. And then you start the clock, and then you create an event listener when the clock is ready. So you create the function called onClockReady whenever your clock cycles are ready. So basically what happens by default, if you use this code here, it would send 10 times your request to the Electro servers, and it runs the logic that we discussed, basically calculating, sending 7 packets, getting rid of the outlier values for the latency, and then calculating the average value for the latencies. And when this application is done and the latency is calculated, the clock ready event is fired. And then you can calculate the server time by calling clock.time. When you use the clock.time in your code, you can essentially calculate and get the values of the times on your server. So now with the logic that is implemented within the clock class, that you can synchronize your time based off of the server time, you should be able to look at how now you can create a time-based movement. This is a very important concept for us to do, because this synchronization allows essentially uniform rendering of the objects across multiple clients in the server. So to calculate or essentially to be able to build a time-based movement mechanism, we would have to look at the physics behind the movement and come up with a mechanism based off of the equations for your motion, or rather a predictive movement pattern, to implement classes that you could call up in your projects and be able to perform this time-based movements. There are 2 things that we will discuss. One is called the converter class, that takes care of your predictions on the movement, and then the heading class that takes care of how you can essentially handle a sort of smooth moving patterns on all of the clients that are synchronized with your server. So when you look at how things move, you essentially turn to physics, or basically the classical equations of motion. These equations are used to calculate at any given point the place or the locations of an object based off of its current speed and its acceleration. And if you open any elementary physics book, you will be able to see all these equations in 1, 2, 3, and n dimensions. If you're looking at a two-dimensional example, for example, in this figure to the left here, you have an object, the round circle here, situated at x sub 0 and y sub 0 in the x and y two-dimensional space, and it has a velocity which we represented by a vector v, and the vector velocity is also composed of a velocity vector across the x-axis v sub x and the velocity across the y-axis v sub y. The way that the movement of this object is essentially restricted is based off of the two-dimensional equations of motion. It's decomposed into two equations. One equation that governs the movement across along the x-axis, and the other equation governs the movement across the y-axis. So if your original location for your object was x sub 0 and y sub 0, then at any given time t, the x value or the position of the x-axis of the object is going to be x sub 0 plus v sub x times t plus 1 over 2 times a sub x times t squared. That is its original location along the x-axis plus its velocity along the x-axis times t plus 1/2 of its acceleration along the x-axis times t squared. The same applies to the y. So its location on the y-axis will be its original location on the y-axis, y sub 0, plus its velocity along the y-axis, v sub y times t, plus 1/2 of its acceleration along the y-axis times t squared. Based off of this equation, you will be able to exactly predict where your object will be at a given time, given its speed and its velocity, if the speed and velocity are constant. So essentially, if nothing else changes, and the only thing that changes is time, you can predict the value of objects' locations, which is called the predictive movement. Time-based movement can be really good, and you could do great stuff with it. You will be able to handle many objects at once and show them in the same spot for all of the clients that have up-to-date information. By using this time-based movement in your game, you will be able to essentially render consistent-looking objects across your platforms and your clients. However, there are a couple of challenges that you would have to discuss and work with. If you were to show exactly where your object is supposed to be based off of the equation of movements, then on your client screens you would see some glitches. Basically, let's suppose that here you have two clients, client A and client B, and client A, let's say that fires a bullet that would travel 150 that would travel at a certain velocity. And let's suppose that the speed of your bullet is 100 pixels per second. So if the client A fires the bullet, in 1 second the bullet will be 100 pixels to the right of your gun that fired the bullet on client A. However, if it takes 150 milliseconds for the message from client A travel to client B, by the time that your message has traveled to client B, and your client is essentially showing that or rendering the equations of motion on its screen, you wouldn't be able to see a smooth movement pattern on client B. What you will see is that at 1 second there's nothing, and 150 milliseconds later there's a pixel that's 15 pixels away from the bullet from the client. Here's the example. So here's the gun. Client A shoots the bullet, and at time 0 the bullet is here. At time 75 milliseconds on client A, who fired the bullet is going to be in the middle here. And at time 150 milliseconds, your bullet is going to be 15 pixels away from your gone. However, client B, before the 150 milliseconds passes, has no idea that client A has fired a bullet. So you won't have a bullet here, you won't have a bullet here, but at frame 150 milliseconds, your client B receives the message that client A had shot a bullet 150 milliseconds ago, so your client will be able to render exactly where the bullet should be, but before that you would not see the bullet. So this is called blipping. Now, to remove blipping is the place that we use latency hiding. Latency hiding refers to a technique that we can use to provide a smoother game experience by minimizing the effects of latency, essentially by being able to interpolate the location of objects, moving objects, before we have the actual position of the objects, so that we could render their exact location. What we want to achieve is be able to predict a combined smooth course correction that our objects can converge to, and based off of that they can actually move towards their actual location when we receive that information from the server. So by looking at this, we will be able to move our objects from their last known heading and update that heading to where we just received. So in the meantime, we can interpolate their location. If we do this update too slowly, then the screens will not be up to date enough to consider actually being synchronized. And if we do this far too quickly, then we will see a lot of jitters in the screen, and we'll essentially end up with jerky movements. So it really depends on our game about when it comes to calculating the speed or the smoothness of our convergence. So if you look at the picture here on the right, in the graph on the right, you would have again a two-dimensional space x and y, and your object, which is the solid black dot here, is the current location and the heading of your object in a game. And let's suppose that if you wait for the latency or the time that you would receive the actual heading and location of your object, you would end up with the actual location, which and the heading, which is at the bottom here, the blank screen, or actually rather the black circle, white circle, and its actual heading pointed out to the right. Now, the idea about our latency hiding pattern is to calculate an intercept line, which is a linear line from where the object was before and where the object is when we actually receive an up-to-date information from the server. And in the meantime, we'll be able to kind of update that as we go on, which basically is again using the equations of motion. There are four methods for calculating smooth paths. The simplest method, which is shown in the picture here on the left, we call it method 1, is suppose that on the x-axis you have the time and the y-axis you have the speed of your object. So the vertical dashed line is the intercept line, is where the positions are actually matched. So the first possible way to resolve this or to hide the latency is to start with the speed of 0 and then keep increasing that speed as we go on until we actually see the true speed of the object, and at which point we basically merge or converge those two values with each other. So the vertical dashed line is where the actual positions are matched. One of the issues with using this linear movement or linear interceptor is that when the paths converge, you essentially would have a drop at the speed from which your interceptor calculated. The second method, basically just picks up a constant velocity, which is the velocity of your object you had before, and you keep that until you receive an updated information from the server, or where the positions are matched, and then you change that speed to the actual speed, or the true speed. This looks like it could have a similar quick change in the speed as we described, but if the object isn't accelerating dramatically, this approach essentially works well. Basically, for constant accelerations, this object would give you smooth paths without jerking that is noticeable, or jerkiness that is noticeable. There are two more elaborate mechanisms to deal with your speed convergence, and that is to allow your interceptor to change the speed and recover that change of speed as you receive some more updated information. And so you can see you can use that either in a linear mechanism shown on the picture in the upper left, or as a nonlinear or Bezier curve matching, which is on the right hand side. The Bezier curve approach will probably result in the best looking smooth paths for latency hiding, but it's very computationally much more computationally intensive compared to the other methods. Now, latency hiding was one potential issue that we discussed. There's another issue, and that is the acceleration that we need to look into when we are trying to calculate time-based movement and synchronization, or time-based synchronization. Suppose that you have client A and client B that are controlling cars in a game. Let's suppose that client A drives the car at a constant speed, say 100 pixels per second, and client B shows the client A's car perfectly as long as the speed doesn't change. If client A stops immediately, an issue arises with your time-based synchronization movement. The issue is like this. By the time client B receives the information from client A that the client A has probably stopped from moving forward, your client B is still updating the movement of your client A. So it would have to move your car ahead, and when it actually receives the actual stop motion, you would have to inverse or convert the movement pattern. So you would have to apply negative acceleration. And the problem is shown in the picture up on top here. Let's suppose that at time t sub 1, client A is moving forward and client B is rendering the car that is moving forward. At time t sub 2, client A stopped the car. So as you see, car has been stopped, but client B has not received the motion stopping from client A because the message has not traveled enough to get to client B. So client B still renders your object. At time t sub 4, client B receives that the client A has stopped, so it would render the two the actual location of client A's car. But in order to come up with a equation that results in the movement pattern, at time t sub 3, your client B would have to make client A's car drive backward until it reaches the actual position. So this problem is the problem of reverse acceleration when it comes to your smoothed movement pattern, or the predicted movement pattern. The solution to this problem is to apply acceleration. If we do not allow client's A car to stop immediately, but rather smoothly decelerate from its speed to the speed of 0, we will be able to adopt that deceleration process until the client reaches the correct location. So at time t sub 1, we have client A's car and its image on client B to be predicted accurately, and at time t sub 4, we have the actual position of the two cars and the cars being stopped, so their speed is 0. However, in client A's movement, it decelerates to a 0, and in client B's movement, it interpolates that deceleration until it reaches the speed 0. So this essentially takes care of this problem. So the way that your books classes address these issues is by introduction of two classes, the heading class and the converter class, both of which you can find under the COM Gamebook Utils Network and Movement packages. The converter class basically handles the smoothing algorithms. It keeps track of three headings. The course, which is the most up-to-date true heading of an object as soon as new information is arriving from the server about the object. The interceptor is the heading that sends the object in a direction and at a speed such that it will smoothly converge to the true heading. So this can be thought of the four approaches that I was talking about earlier. And every time the course heading is updated, the interceptor heading is recalculated. And the view is actually the heading that is updated every frame to use values from the interceptor or the course to represent where an object should be shown on the screen. When it comes to the time to move the visual representation of the object on the screen, the application uses the view heading, not the interceptor or the course. So the course is the actual up-to-date information. Interceptor is what calculates where the information should go, and the view is where you can look at and see where your objects should be shown on the screen. To use an instance of the converter class, basically, you can essentially control the position of an object, such as a car or a bullet or a walking alien. You would give the moving object a converter class instance, and then you'd be able to expose that to update the information. In every frame, the run method will basically call the converter and update the view headings, and therefore you can actually deal with the convergence. So let's take a look at an example. Right, I first need to run my Electro server. And then you would have to see the Electro server port and IP set up correctly. Alright, so now that the Electro server is set up, notice that the way that this program works is essentially at any given time, the car class looks at its location and the mouse's current location, and then try to move the object around. So it accelerates until it reaches close enough to the mouse position, and then it decelerates to a stop. And as you see, the shadow of the car that you see here is basically where the location of the car is in other clients. So let's suppose that we run another example of this. Now this is the second car, and as you see, the location of the car is being updated on my other screen. So on the screen in the middle, I have the car and its shadow, and in the screen on the left, I have the car location being updated from the server. And as you see, there are certain amounts of jerkiness to the car pictures, but the car basically picks up, accelerates, and then it decelerates to a stop. Right, so now what happens in the car class you'd essentially initialize your car. In the constructor, you create a converter class. You set its intercept multiplier, say, to 7, and then the maximum duration intercept time to 2000, and then in the run, you basically, in your car run, you run the converter function dot run, and then you update your x and y positions to the converter.view.x and converter.view.y, and then you calculate the rotation index, which is basically, in this special example, you have 36 different views of the car for every 10 angles, or 10-degree angles, and then from the rotation index, like where your car should be headed, the angle of the car, you will calculate that, and then you would run to that heading, which comes from your converter.view.angle. And remember, the view was the part of the converter class that had the actual view of where the objects should be and should be rendered. So the car example object here basically takes care of creating your event listeners, joining rooms, sending a public message, and updating the users list. It creates a room request called car in the zone car, and then applies your objects or your cars, logs them into the view, and then it basically updates the headings of the cars, it moves all the cars, and then it updates or sends the updates to the server if 250 milliseconds has passed, or if the car course has basically changed, or any acceleration of the car has been changed. And so this class would take care of all that movement patterns for you. You have an acceleration function and a deceleration function, which basically takes care of your speed, your time for the acceleration, and then it calls up on the converter course acceleration, and then at any given time sends the updates to your server. Let's take a look at your update heading. Okay, in the update heading function, you basically to see if check to see if it's okay to update your information. You check the mouse position, and based off of that, you can calculate the angle at which your car is pointed, and then you basically call up the run of your car, which takes care of moving the car, as I explained earlier. So if the speed is positive, then you set the angle, you set the car location in the course, and then you set the clock time of your server, which we discussed earlier, to the course time. And this would take care of the rendering of your objects. And finally, in the format heading, you calculate and you basically put all those information, like the heading X, heading Y, heading speed, heading angle, time, acceleration, time, speed, and the player name into an electroserver object, and then you would send that object to your server. And then when on the client an update event handler is called, you read the heading, name, X and Y, angle, time, speed, acceleration, time, and end speed from the electroserver object, and then you set those up, and based off of that information, you render all the pieces of information on the screen of your client machine. and eventually you call up the converger.intercept on the path that you calculated for all the cars that were not the current car or the current client's car. For the current client, you can calculate the information locally. For the non-current cars or the cars that don't belong to the client, you parse out the electroserver object information such as heading, time, acceleration, speed, and everything, and then you call the intercept method of the converger class, and you get the path to it for it to calculate your physics that we just described earlier in the class. So this is basically the car class object, and let me just run the alien class also, or the alien function. The function is basically the same. The only difference is that your converger is set up in your the guy class. In the frame-based class, we did not use a converger, so basically we updated every information frame by frame. In our in the time-based movement for the aliens class, in the guy class, guy constructor, we basically set up a converger class. We said it's intercept multiplier and intercept time, and you notice that the values here are less than the values for the car class, because in the car class you have 7 and 2000, because cars movements are much more fast than the aliens movement, which is slower, so you can get away with smaller values. And the rest of the functions are pretty much the same. The angles that we use here are 8 angles depending on the composition of keys. With the car, we had 36 different views of the car's angles, but aside from that, everything is basically the same as far as the classes are set up. And so here's an example of the alien object, and I'm just going to run 2 sets of examples of the alien object, and I'll just show them side by side. So as you see here, when one alien moves, in my local screen on the left, you see the shadow following it, and as you see in the screen to the right, which is the other client, you will be able to update this information. On the other client side, you would see some jerkiness a little bit, and as I said, but essentially you would be able to smoothly configure the locations of your objects. Now I'm moving the alien on the right hand side, and as you see, the shadow follows it until it reaches its location, and on the left hand side picture you see the actual alien being moved, and the converger class takes care of predicting the motion based off of the time. So this is pretty much it. I will basically put the examples of the classes for the time-based alien movement and a time-based car class, and I want you to run them and to go through the code and look at the code and the implementation of the converger class, and try to play with the parameters and get a sense of how these classes are integrated, and basically you should be able, based off of these, write other examples or other classes that you can use and integrate in other kinds of projects. So with this being said, I think we are pretty much at the end of our time-based movement, and there are certain mechanisms and ways that you can create a better converger class. At this point, your converger takes care of and does a good job of synchronizing the positions based on the prediction and the smoothing parameters that we talked about earlier. The heading updates is basically updates the angles property by using an easing equation to have the angle quickly match that of the interceptor or course headings. This can achieve a smooth rotation, but may not give you a good match of up to the direction of the objects that are moving. Your objects can stop or rotate as moving that this wouldn't take care of. So you may be able to kind of take a look at implementing another kind of converter class or methods on the converter class that take care of different situations. Another improvement that you can use is basically instead of having the actual value of the movement and just using them as constant speed values and then updating them every time you have a value for them, you can use Bezier curves or linear interpolation mechanism to accelerate and decelerate your objects to match with the actual locations when you get the values from the server. So this being said, I think this should cover the time-based movement and complement our frame-based movement mechanisms. And we have one more item to discuss, and we'll talk about this next week before we finish up our class, and that is building and creating a lobby system for your multiplayer games so that the players would have a mechanism or a way to kind of look around in the content of your game or in the basically lobby of your game before they join a specific room or a specific area of your class. And we'll use a variation of the dig game as a lobby system mechanism. And so you can establish that in, say, the car example or alien example. So different players come in and they will be able to set up a game room and join certain game rooms or invite certain players to join a game and so forth. And that would cover a good deal of working with essentially multiplayer game setups. Certain aspects that we will not be able to discuss this semester is to look at some artificial intelligence techniques that you could use for pathfinding cooperative gameplay and essentially competitive gameplay. And those I think would be best left to a class such as an artificial intelligence for games. And we will discuss those in more detail. So I hope that you enjoyed this class, and I will talk to you next week.